Hello, I'm Alexander Harrowell. I'm a principal analyst at Omdia. I cover advanced computing, which is our term for all things AI semiconductors. Today, I'll be talking to Matthew Formica, who's the Senior Director, Head of Edge Product Marketing at Intel. So, good evening, Matthew.
Hi, Alex. Great to be with you. Glad we have this chance to chat.
Okay, so AI has been deployed out to the edge far longer than you think. Computer vision is probably the first of all the AI applications to be in production for real. But in the last 2 years, though, as with everything in AI, there have been changes. A new class of small language models has emerged, which put a much bigger range of capabilities into the kind of model weight class that can run well on PCs, edge devices, and embedded systems. That's from around 500 million to around 8 billion parameters. A lot of people will tell you that physical AI is the next big opportunity after agentic AI. Now, one way to do this is just to deploy GPUs, but when we do this, we bring in new levels of capital expenditure, we bring new levels of power draw and thermal load, and we bring in greater levels of complexity in software development, deployment, and maintenance. Once you deploy a new microarchitecture, a second microarchitecture, you of course need a second compiler, SDK, tools, and a new range of developer skills. And of course, with all things out of the edge, deployment and manageability are big problems. Now, unless we can resolve these issues, it's disturbingly possible that edge AI may always fall behind as an investment priority. We recently did, here at Omdia, a market survey called the AI Market Maturity Survey, where we found that it was surprisingly low as an investment priority. So we have some problems, and I hope, Matthew, you have some solutions.
Yeah, I agree with those problem statements. It is more complex at the edge to roll out some of these solutions than in other markets. Of course, AI is new everywhere, and it's, fits and starts getting adopted. But the fact that at the edge, AI has to integrate in with a lot of existing infrastructure, some legacy infrastructure, it's got to be in place for a lot longer. There's a much more diverse set of requirements, mean that it's worth it to take a little more time to be thoughtful up front about your architecture of your solution so that you have something that is really going to be practical, not just an interesting POC. And we have seen this beginning of an inflection point away from traditional computer vision, which is still very popular in deployment, to these new class of models that are really bringing Gen AI to computer vision. And it's very interesting as Gen AI has evolved, that has started to mean for the edge.
Yeah. So what examples have you seen of those new small language models getting deployed? Things such as, Llama 3.8b, Gemma 3, the new QN, the new small ones among the new QNs.
Yeah. So feels like almost every day there's a new model that's released. It's hard to keep up with them all. Certainly, there are very popular ones across the industry, like you mentioned, Llama 3, 8 billion, right? They have up to 70 billion parameter flavors, but it's typically that smaller version that is adopted. At the edge, the traditional LLMs get used for machine data processing in manufacturing, or a variety of situations where you have status information that needs to get crunched. What is often more popular, actually, are vision language models. And these are the models that are trying to do Gen AI work on computer vision data. And these are perhaps less well known because they don't find their way into other industries as much. But at the edge, they're kind of really the sweet spot. And so there's models like Qwen2 VL, which is a 7 billion parameter vision language model. And the neat thing about these models is that they take sort of a front end model architecture of computer vision and attach it to a back-end LLM style architecture and basically treat details about the image as if they're words, as if they're tokens. And so then it can reason about what's in the picture, what's in the video. And that's where we're seeing some of the most interesting innovation for the future.
And what kind of an impact is that having on the demand for compute in those deployments?
It's having a big impact. So if you think about the models that have powered computer vision at the edge for the last 10 years. You take a YOLO model, for example, very popular. these models are typically less than 50 million parameters in size. So if you take that and you think about the latency requirements, typically less than 15 millisecond response time is what's required, less than 10 millisecond in many cases for real time. Robotics requires sometimes less than 1 millisecond response time for real time controls. And so you think, okay, how much work can you do in that fraction of a second? And you take a 50 million parameter model and you say, great, we can deal with that. Now we have a 500 million parameter model or a 5 billion parameter model, and you're up a couple orders of magnitude. And so you need a significantly greater amount of compute in the system to be able to process those still at that super low latency. And so that is driving a significant increase in compute demand for AI at the edge.
I mean, there are quite a few of these robotics projects now that have like two levels of processing. So you have a so-called vision action language model to do that does high level movement planning, and then you have a small one that's generating control signals to execute that, running on a much faster loop.
That's very true. There are a variety of architectures being innovated. High-end robotics do typically have a controls function, often with one processor, and an AI and perception function, often running on a separate processor with a separate stack, just to keep everything moving in time. And you're right, even on the AI and perception side, sometimes they're not doing the work with just one model. They're actually stringing together a pipeline of models that all have to work in order for the robot to understand its environment and figure out what to do next.
And that's the kind of architecture. One of them is likely to be performance critical, and one of them is likely to be latency critical. So which has some impact on which of various kinds of cores you might have access to, you might choose.
Absolutely. And so the software architecture to stitch this all together gets complex as well. Probably robotics is at the cutting edge of this work. It's some of the most complex work. And within robotics, parts of the robotics industry are more mature, parts are less mature. There are really three types of robotics. There's stationary arm, in manufacturing and so on. That's a fairly mature market. There's AMRs, autonomous mobile robots. These are ones that will go around in a warehouse, for example, move packages around. That's new and growing quickly and relies on that AI and perception piece. And then there's what all the excitement is about, which is humanoid robotics, which are not widely deployed yet, but are incredibly interesting for testing out the edge of capability in this space and showing where the industry is going over the coming years. And so we're seeing that's where the envelope is being pushed. There's a lot of other use cases and industry segments that are frankly easier to design for and will probably reach wider deployment more rapidly.
Yeah, the big difference between something like YOLO and one of these more modern models is that the new ones have a much wider range of capability. You can, as well as programming through prompt. They also have multimodality. They also have multimodal input and also multimodal output. So, can you give us any idea of the applications that you're seeing? Beyond more specific than robotics, for example.
Yeah. So I would say, the technologist in me finds the architecture of the model interesting, but ultimately what matters to business is what can you do with the model? And what these new models do that the old models couldn't is two things. One, they have better understanding about the context of what's really going on in the scene. And what that means, secondly, is that the model is less fragile. It doesn't break as easily. And so a couple of examples that we're seeing a lot of POCs in right now. One example is in retail, where you have order accuracy checking, often for takeout, and you might have a camera pointing at the person who's loading the food and other items into the bag to make sure that they don't forget to put the spoon in or put napkins in or make sure that they got the soda correct, for example. And that system is automatically comparing the receipt of what was ordered against what they're actually putting in the bag. And from a solution perspective, this is not a brand new idea. And there are implementations that use traditional computer vision. The problem with those is that when the packaging changes color or something changes about the menu, with those traditional models, the model breaks. You have to retrain, that system goes down, it can't adapt. Whereas with these newer models, because they have more context, even if the soda changes colors on the package, it can still tell that's a soda. And so it's able to keep running and keep the business going more easily and adapt to changes. We're seeing a similar thing in worker safety, where for many years there's been solutions in factories to detect, do workers in certain areas have hard hats on? Do they have safety vests on? The problem with those traditional models is that if the safety vest changed color, the model might break. Again, these new models with a lot more detail and a lot more contextual understanding still can understand it's a safety vest, even if it's a different color. And so there's a lot more resiliency in those models.
Yeah, I think my favorite in that line was a product from one of the Chinese hyperscalers that is capable of telling if chefs are wearing their chef hats or not, which seems very specific. But you see what we mean.
Yes.
Anyway, I'm aware of some edge AI deployments that use surprising numbers of GPUs. I mean, I was thinking in terms of, it was a while ago, there was 16 relatively small ones per location, which then got consolidated down to, I think, four medium, mid-size ones. Is this really realistic in terms of expense, in terms of physical security, in terms of power draw, in terms of heat?
Yeah. In a few cases, it's required. I'm not here to say that it's not sometimes needed. There's a wide diversity of architecture and approaches at the edge. But we see the sweet spot as systems that have integrated AI acceleration right into the main processor. And the reason for that is some of the things you mentioned. A lot of these businesses that need these systems can't afford the capital budget to outfit a bunch of high-end GPUs in every retail store or every factory line, et cetera. And so they're looking for more cost-effective solutions. Secondly, there is often already an existing form factor that the compute needs to fit into, whether it's an industrial PC or a robot or a retail point of sale or a variety of other form factors. We track well north of 100 of them in our business. And those form factors can't accommodate something that's much larger, that has heat sinks and fans and extra cooling, et cetera. And so you have to figure out, how do you do the work in this constrained form factor that you have? And that's really important. And then you mentioned power, of course. If you're going to be running this, many edge systems aren't running the way we use our PCs 8 hours a day. They're running 24/7. And you don't want to replace them every few years like you do your PC. It's got to be able to run for 10 years. And so 24/7 for 10 years, think about the power draw of that, of maybe a couple 100-watt discrete GPU versus doing everything, within, say, a 65-watt envelope of a main processor. And so that power draw can get quite expensive over time at scale. And then some solutions, especially in places like manufacturing, can't accommodate fans. They're actually fire risk in certain environments. And so there are requirements that they be fanless. So you actually can't put a discrete GPU in those solutions.
It was quite an effort to do fanless PCs in the first place. I remember that was seen as a real achievement.
Yes.
But now we're going backwards on that.
Yes. And again, sometimes the compute demand is so high that there's no way around a discrete GPU. And so they have their role, their place to play in the ecosystem in the market. But a lot of cases don't. And so probably folks should assume that in most cases, they don't need a discrete GPU. And in fact, they'll save a lot of money and architectural solution design by skipping it.
Intel has decided to launch the Panther Lake PC products on PC and for edge systems at the same time. Is there I feel there's a conclusion I should take away from that.
Yeah, the conclusion is that the requirements for the edge around AI are accelerating, and our need to get into market faster is increasing. And so rather than do what we've historically done, which is we launch a product for PC and then some quarters or even a year after we launch the edge derivative of that, the edge flavor, we've now upstreamed all of the edge requirements right into our upcoming Panther Lake Core Ultra processor, so that it is date and time launching with the AI PC variant. And so that enables our edge customers to get their hands on this level of AI compute, significantly more AI compute than our prior generation product, much, much sooner than they have in the past.
Yeah. How does it, for example, help with the operational issues we were talking about? So manageability, deployment, DevOps.
Yeah, so the Panther Lake architecture has many innovations over our prior products, and some things that stay the same, thankfully, that stay the same. So from an innovation perspective, we've increased the AI compute capability on the product by roughly 80% gen over gen. So that's a massive increase in the amount of TOPS or measure of compute available. Additionally, the CPU architecture within that processor has advanced to have much more sophisticated power management. And so you actually can be more efficient whether you're running in a mobile device that's battery powered or when you're plugged in to the wall. And this product has the consistency of having Intel's traditional manageability solutions built in, including vPro, which is really critical in a lot of edge environments, because the most expensive thing you could do is have to send a crew out in a truck to repair a device if it freezes. What you really want to do is be able to just remote reboot or even remote troubleshoot that device. And that's what vPro enables. And all of the SKUs that we sell at the edge for this upcoming Panther Lake product have vPro built in. And so we're excited to continue to provide that capability, that key manageability capability for our customers.
Yeah, and so as we're coming to the end of our time here, could you give us, for example, an example of a customer for this?
Yeah, so I expect that we will see these new models ultimately adopted by all of the customers who are using traditional computer vision today. It will, over time, become the predominant way that AI is done at the edge. And so when we look across industries, we have deployments with a lot of medical device and medical imaging companies, with manufacturing companies, smart cities. We have several pilots going on with cities around the United States right now, where they are evaluating this new Gen AI plus computer vision technology I talked about for emergency management. How do they more efficiently analyze what's happening at an intersection and get the right emergency management services there? It requires that greater contextual and awareness that I talked about to do that. And so this is not something that just a few customers will be able to adopt across every industry at the edge. The promise of traditional computer vision will be further increased by these new Gen AI and physical AI capabilities. And we're excited to see what the whole industry is going to be doing with these.
Thank you very much, Matthew.
Thank you. Great chatting with you today.